The ASIF external fixator is a universal system consisting of various modules. The tube fixator with the tube-to-tube standard assembly. The hybrid ring fixator. And the pinless fixator. The external fixator for segment transport is a special application. This presentation will demonstrate the three basic assemblies and the segment transport to the tibia. The basic elements are cell drill shank screws, Steinmann pins, steel tubes or carbon fiber rods of different lengths, open adjustable clamps, which allow the free placement of the shank screws, tube-to-tube clamps, and a transverse clamp, also called a metaphysial clamp. The following instruments are required: the compact air drill with the chuck and key, a long and a short version of the drill sleeve assembly, the universal chuck with T-handle, and a socket wrench or a combination wrench. The tube fixator, modular standard assembly with tube-to-tube clamps. The external fixator with tube-to-tube clamps permits secondary correction in all planes, and is therefore regarded as the standard configuration of the tube fixator. The position of all shank screws can be freely selected to accommodate the soft tissue situation. The fracture is reduced approximately, and the bone is fixed in the clamp. The first two shank screws are inserted into the proximal fragment. The drill sleeve assembly is inserted through a small stab incision until the bone is reached. The trocar is removed, and the first 5 mm cell drill shank screw is inserted with the air drill into the proximal cortex. Thanks to the geometry of the cell drill shank screws, the tip is only countersunk into the opposite cortex, avoiding complete perforation of the cortex. A conical step in the screw core will affect radial pretensioning, which results in improved anchorage compared to the conventional screws. After perforation of the proximal cortex, it is advisable for beginners to remove the air drill in order to avoid perforation of the opposite cortex, and to insert the screw manually into the opposite cortex with the universal chuck with T-handle. Length measurement is unnecessary. The distal shank screws are inserted in the same way as the first ones, taking care to avoid the anterior tibial tendon. Two open adjustable clamps are mounted on a short rod. The clamp can be slid on the rod like the old adjustable clamp. The main benefit of the open adjustable clamp is that it can be mounted on the rod laterally, for example, for the subsequent reinforcement of a completed frame. The assembly is then fixed to the shank screws in the proximal fragment. The same is performed on the distal fragment, regardless of the position of the rod. The two rods are now connected using a third rod and two tube-to-tube clamps. Any correction can now be carried out using the rods as handles. Once the reduction is completed by the surgeon, the tube-to-tube clamps are tightened by the assistant. Stability is achieved with technical simplicity. This modular assembly has become a standard configuration today. Its advantages are the free choice of screw position and the opportunity to correct in all planes. Dynamization of the assembly with tube-to-tube clamps. An additional rod is mounted parallel over one fragment. The nuts on the lower rod are removed and replaced by special cap nuts marked dyne, allowing the rod to glide within the locking sleeves. This permits controlled movements of 1 to 2 millimeters in the longitudinal axis to improve the adaptation of the fracture fragments. For an approximation of the fragments over a longer distance, the shunt screws must be placed parallel in at least one fragment. A rotational correction can also be performed. Rotational stability is achieved by connecting the two rods with a universal joint. The lower nut is tightened. The upper nut has been replaced by a cap nut marked dyne. This allows axial gliding while retaining rotational stability. In this computer animation, the cap nuts marked dyne, in other words the loose nuts, are colored blue. The hybrid ring fixator. This fixator is applied to very proximal or very distal fractures of the tibia, with or without injury to the joint, where the articular block is too short to accommodate two shunt screws along the longitudinal axis. The X-ray shows a fracture which is suitable for treatment with the hybrid fixator. The additional components of the hybrid fixator are open rings of various sizes, including a full ring. The rings are made of aluminium in a double T construction, which ensures high bending and torsional stiffness. Adjustable connecting clamps. Wire pin to ring clamps for the fixation of the K-wires or shunt screws to the ring. Ring to rod clamps for the fixation of the carbon fiber rods or steel tubes to the ring. Kirschner wires with spade point tip and reduction wires with olive and spade point tip. The olive permits exertion of interfragmentary compression and increases the stability in comminuted fractures. These additional instruments are required. The slotted tissue protection sleeve for K-wires and the slotted tissue protection sleeve for shunt screws. After placement of the K-wire or shunt screw, the slotted tissue protection sleeve can easily be removed from the side. With the wire tensioner, the K-wires can be tensioned as required. The hybrid ring fixator will be applied to a fracture of the tibial plateau. The slotted tissue protection sleeve is inserted through a stab incision through the soft tissues until the sleeve reaches the bone. The first wire is positioned on the bone and with the compact air drive is inserted into the tibia parallel to the tibial plateau. Once the wire has penetrated the opposite cortex, the air drill is removed and the wire is pushed through the soft tissues by hand until it extends from both sides at an equal length. The reduction wire with olive is used to achieve interfragmentary compression. The slotted tissue protection sleeve is removed during insertion, and the wire advanced until the olive touches the bone surface. An adjustable wire pin to ring clamp is placed onto the end of the wire. After the ring locking nut has been released, the clamp is attached to the ring. This procedure is repeated on the other end of the wire. The ring locking nuts and the wire locking nuts are tightened. Additional wires can be inserted directly through the clamp, whereby the clamp can serve as an aiming device. An additional adjustable wire pin to ring clamp is placed over the other end of the wire and fixed to the ring. The angle between both wires should be as wide as possible, and the second wire should be placed more distally. The wire tensioner is pushed over the wire. The wire locking nut on the same side as the wire tensioner has to be loose, while the nut on the opposite end of the wire has to be tight. The wire is tightened by turning the locking sleeve in a clockwise direction. The degree of tension is indicated by the scale on the wire tensioner, which shows 50, 100, and 130 kilograms. Once the required wire tension has been reached, the wire locking nut can be tightened. The wire tensioner is removed by turning the locking sleeve anti-clockwise. These steps are repeated to tension further wires. A unilateral half frame will now be mounted onto the distal segment. To achieve greater rigidity, the rod lies as close to the bone as possible. The ring locking nut is removed from the ring-to-rod clamp. The clamp is pushed onto the rod, and the threaded post passed through the nearest hole in the ring. The ring locking nut is again placed on the threaded post and tightened. The open adjustable clamps on the carbon fiber rod are tightened with the socket wrench. The segments are reduced using the ring and the carbon fiber rod as reduction handles. The nuts of the ring-to-rod clamp are then tightened in order to stabilize the two fragments. The wires are cut and bent. The white protective caps are placed on the wire ends. For added stability, a delta configuration can be constructed by adding a second rod. The rod is stabilized at the medial section of the ring with a second ring-to-rod clamp and fixed to the distal shunt screw with an open adjustable clamp. Alternatively, the distal ends of the rods can be fixed tube-to-tube clamp. The stability of the standard frame can also be increased by placing a shunt screw in the proximal fragment. Depending on the fracture situation, a 5mm cell-drill shunt screw can be inserted through the large aperture of the wire pin-to-ring clamp. The frame can be assembled in the same way for the reduction of fractures of the distal tibia. The pinless fixator. The pinless fixator is designed for fractures of the tibia with severe soft tissue trauma, where a tibial nail may be planned. Nailing can be performed with the fixator applied. The pinless fixator does not penetrate the medullary canal. It is designed as a temporary stabilization device and is therefore not stable under load. Extension treatment is a further indication for the pinless fixator. The pinless clips available are small, asymmetric, and large. After removing the fixation post, the handle is placed on the clip and the knurled nut tightened. If the clip is difficult to open and close, the hinge nut on the opposite side of the handle can be loosened. The tips of the small clip are placed in the frontal plane of the distal tibia. While the handles are pressed together, the trocar tips are anchored in the cortex with rocking motions. In dense cortical bone, the clip must be rocked 5 to 8 times. The position of and tension on the clip are secured by tightening the nut. The handle is removed and the fixation post mounted. The asymmetric pinless clips are designed for applications at the middle third of the tibia. This clip has a bent arm with a double-pointed tip and a straight arm with a single-pointed tip. The position of the clip is shown on this cross-section of the middle third of the tibia. The bent arm is placed on the frontal tibial crest, while the straight arm is placed posteriorly through a medial stab incision. The correct placement of the asymmetric clip is now shown on the bone model. The double-pointed tips may not be anchored by rocking motions, as is recommended with the small and large clips. The clip is fixed by tightening the hinge nut, and the handle is replaced by the fixation post. This procedure is repeated for the second asymmetric clip. The large clip is used at the proximal third of the tibia, or where there is considerable soft tissue swelling. The large clip is placed and fixed in the same manner as the small clip, by pressing the handles together and applying the clip with rocking motions. The fixation post is then mounted and tightened. An open adjustable clamp is mounted on each fixation post. The clamps are connected with an 11mm carbon fiber rod. Alignment of the fixation posts allows all 4 pinless clips to be connected by one rod. The pinless system is stabilized by tightening all clips and clamps. By performing an osteotomy between the 2 middle clips, a secondary fracture reduction can be demonstrated. The clamps and the fixation posts of the 2 proximal pinless clips are loosened. The proximal fragment is now 3-dimensionally adjustable. After reduction of the proximal fragment and tightening of all nuts, the stability of the fragments can be examined. The correct placement of the clips will now be demonstrated on this soft tissue model. The asymmetric clip, which is to be applied to the middle third of the tibia, is positioned through 2 transverse stab incisions, one on the lateral aspect of the tibial crest and the other on the posteromedial border of the tibia. In the first step, the straight arm of the clip is inserted anterior to the flexor digitorum longus on the posterior-medial border. The bent arm is positioned on the tibial crest. The remaining clips are applied as shown before. The pinless clips are connected with a rod. If nailing is planned with the pinless fixator in place, the rod must not hinder access to the insertion site of the tibial nail. the external fixator for segment transport. Finally, we shall present a special application of the tube fixator. The segment transport fixator is a modified double tube configuration. In addition to the long rod, we also require a threaded rod, onto which 3 short tubes are mounted. The rods are held in place by hexagonal nuts and a transport nut. Assembly is the same as for the double tube fixator. The 2 outer cell drill shunt screws are inserted first. The threaded rod with 5 open adjustable clamps and a transverse clamp are attached to the 2 shunt screws. A rod with the same number of clamps is now mounted onto the shunt screws. A second proximal shunt screw is inserted through both transverse clamps into the tibial head. The nuts of the transverse clamps are tightened. The second distal shunt screw is inserted through both open adjustable clamps. As with the double tube fixator, the threaded rod and the carbon fiber rod must be parallel to each other and parallel to the longitudinal axis of the tibia. The third proximal shunt screw is then inserted and the nuts tightened. 2 shunt screws are inserted into the free bone segment, and the nuts of the clamps are tightened. A segment of approximately 5 centimeters, marked here with a blue rectangle, is resected, creating a defect. The proximal corticotomy is performed between the 2 proximal short tubes. In the bone model, an osteotomy will be performed with the oscillating bone saw. The 2 nuts on the outer clamps above the transport segment are removed and replaced by the cap nuts marked dyne. The clamps can now glide along the rod. By releasing the distal nut above the transport segment, the segment can be moved along the longitudinal axis towards the defect. Finally, after docking, even compression can be applied.